Okay, so what would be more fun than solving a system of two equations with two variables? That's right, solving a system with three equations and three variables. So that's what we're going to work on in section 7.2. So the solving techniques we have are substitution and I'll put elimination by addition. Those are the techniques we learned with two equations and two variables. We're going to use these same equations to solve, or these same techniques to solve three equations with three variables. There are other techniques, but this course does not cover those techniques. So I'll talk a little bit about it when we do another section, but this section here, 7.2, we're just going to focus on, I forgot the A. We're going to focus on these techniques and what we've done in the past. Now, because we're going to have three variables, we won't have an ordered pair for a solution. We'll have what's called an ordered triple. Ordered triple. Okay, so you're going to have the ordered triple is going to go x, comma, y, comma, z. Now, they don't have to have the variables be x, y, and z, but I think most of our examples are x, y, and z. Normally, if it's like ABC or F, G, H, they just go alphabetically. Okay, so when we have a system, you might remember we graphed a system with two equations and two variables, and we do that in a plane. We have for what we call a 2x2 system, you have a coordinate system. It's a flat piece of paper. You graph the lines where they intersect. That was the solution, right? Okay, so that's what we did in 7.1. When we have three variables, it's a little bit harder to graph these. That's why I've provided a picture, because each equation represents what's called a plane. You can think of it like a flat piece of paper. So you have three equations, you have three pieces of paper. So one way they can intersect is you could just have them meet in one point. Okay, so one point there that they share. That point there is part of the light green plane, it's part of the orange plane, and it's part of the dark blue plane. Okay, that's what colors I'm going to say those are. And so you get one solution, one ordered triple. Okay, so that's that case. You could have the three pieces of paper or the three planes intersect in a line. So this line here, I don't know if you can see it, that line there, it's part of the orange plane, it's part of the light green, and part of the dark blue plane. And so the answer, the solution, is a line. And if that happens, we'll show you how to write that out. Okay. You could have the three sheets of paper intersect this way. Now in that case, there are no points that are part of the orange, light green, and blue. There are no points that they have in common, therefore there is no solution. No solution. You could have the three pieces of paper intersect like this, where the light green and the orange share some, the dark blue and the orange share some, but there's no points that all three planes share. So again, there's no solution. And you could have this case where you just have three pieces of paper, none of them are intersecting. It's like each one is its own plane. And so there's no solution there. There's no points they have in common. Okay, so sometimes the answer is no solution, and we'll talk about that when we get to it. Sometimes the solution is one point, which is an ordered triple. Those are the kind we kind of like. And then sometimes you could have a solution that's a line. Okay? You might be wondering, wow, we're doing 3 equations and 3 variables. Are we going to do 4 equations and 4 variables? Such things exist. You can have larger systems. I remember somebody talking about a 9 by 9 system once. But that's the study of linear algebra. And we offer that course here at CMC. It's after you take some calculus courses, and then you can take linear algebra. One of my favorite classes that I took. And we have techniques for doing that. When we get really large systems, generally we go to a computer and we program it to solve such systems. But